Hello friends, welcome to the series of lecture of Mathematics 1. Myself Hardik Patel. In the last session we have seen some of the basic concept of partial derivative and total derivative and chain rule. In today's session we are going to take some miscellaneous problem of chain rule. Now, first example we are going to start with, if u is equal to x square plus 2yz and y square comma y square plus 2xz, then prove that y square minus xz into del u by del x plus x square minus yz into del u by del y plus z square minus xy into del u by del z is equal to 0. Now we are starting with a chain rule. We are going to assume that x square plus 2yz is equal to L and y square plus 2xz is equal to M. So your function is going to be of the form f of L comma M. So if you are going to apply the chain rule, then u is a function of L and M, and L and M are functions of x, y and z. So your chain rule will be of the form, for del u by del x, you have del u by del L into del L upon del x plus del u by del M into del M by del x. Now the function is not given, so del u upon del L and del u upon del M remains as it is, and del L upon del x has a value 2x. Same manner del M upon del x has a value 2z. So this is your equation number 1. Same manner del u upon del y is del u by del L into del L by del y plus del u by del M into del M by del y, and del L by del y has a value 2z, del M by del y has a value 2y. So your equation is reducing in the form of del u by del L into 2z plus del u by del M into 2y. Same manner del u by del z will be del u by del L plus del L by del z plus del u by del M into del M by del z. And del L by del z has a value 2y, del M by del z has a value 2x. So you have 2 del u by del L into 2y plus del u by del M into 2x. Now starting with your LHS. So putting the value in LHS, that means y square minus 2 minus zx into del u by del x plus x square minus yz into del u by del y plus z square minus xy into del u by del z. Putting the values of del u by del x, del u by del y and del u by del z, and simplifying it and combining the terms with del u by del L and del u by del M. So you will have del u by del L into 2xy square minus 2x square z plus 2x square z minus 2yz square plus 2yz square minus 2xy square plus del u by del M into 2zy square minus 2z square x plus 2z z square y minus 2zy square plus 2xz square minus 2x square y, and all the terms will be cancelled out and you will have answer 0, that is your right hand side. Hence this proves your results. Now same manner, another example we are going to take is, if r square is equal to x square plus y square plus z square and v is equal to r raised to m, then prove that del square v upon del x square plus del square v upon del y square plus del square v upon del z square is equal to m into m minus 1 times r raised to m minus 2. So instead of this, it may be asked in the form of, if r square is equal to x square plus y square plus z square and v is r raised to m, then prove that nabla square of v is equal to m into m plus 1 times r raised to m minus 2. Here nabla square is nothing but it is del square upon del x square plus del square upon del y square plus del square upon del z square. Now we are starting with a solution. Here r square is equal to x square plus y square plus z square. So if you are differentiating with respect to x both sides, then that will give you 2r del r by del x is equal to 2x, and that will give del r by del x is equal to x upon r. Same manner del r by del y will be y upon r, and del r by del z, that will be a z upon r. Now we are going to apply the chain rule. Here v is a function of r and R is a function of x, y, z. Correct? So V is a function of R and R is a function of x, y, z. So if you are finding del V by del R, then it will be a dV by dr into del R by del x. Correct? Now V is nothing but R raised to m. So dV by dr is m into R raised to m minus 1. And del R by del x is x upon R, that we have already find out. Putting both values and simplifying, that will give you del V upon del x is equal to mx R raised to m minus 2. Same manner, del V upon del y is my into R raised to m minus 2, and del V upon del z will be mz into R raised to m minus 2. Now we are going on to the second order derivative, del square upon del square V upon del x square, that will be a del by del x of del V by del x. But del V by del x is nothing but it is m into x R raised to m minus 2. So if you are differentiating with respect to x, then you have to apply the UV rule. And first, x as it is derivative of R raised to m minus 2 is m minus 2 into R raised to m minus 3 into del R upon del x plus m into R raised to m minus 2 as it is derivative of x with respect to x is 1. Now del R by del x has a value x upon R. So put it and simplify. That will give you del square V upon del x square. That will be a m R raised to m minus 2 into the bracket x square upon R square into m minus 2 plus 1. This is equation number 1. Same manner, del square V upon del y square, that will be a m into R raised to m minus 2 into the bracket y square upon R square into m minus 2 plus 1, and del square upon del z square of V, that will be a m into R raised to m minus 2 into z square upon R square m minus 2 plus 1. So adding these three equations, that will give del square upon del x square plus del square upon del y square plus del square upon del z square of V is equal to m into R raised to m minus 2 into the bracket. Now see, m minus 2 upon R square common from first terms of bracket, that will give you x square plus y square plus z square into m minus 2 divided by R square plus 1 plus 1 plus 1, that will be a 3. So you will have plus 3. But x square plus y square plus z square is your R square. So if you are going to put it R square, then that will give you the simplified term is equal to m into m plus 1 times R raised to m minus 2. So this proves your result. And if you are writing it in the form of nebula, then nebula square V is equal to m into m plus 1 times R raised to m minus 2. Now, we are going on to the example, if R square is equal to x square plus y square plus z square and u is a function of R, then prove that del square u upon del x square plus del square u upon del y square plus del square u upon del z square is equal to f double dash R plus 2 upon R into f dash of R. Now see, here u is not given, only it is given that u is a function of R. And you have given that R square is equal to x square plus y square plus z square. So again we are starting with a R square, or instead of this question it may be asked in a form of nebula, then also the method is going to be same. For solution we are starting with R square. R square is x square plus y square plus z square. So differentiating with respect to x both sides, that will give you 2r del r by del x is equal to 2x. 2 will be cancel out, and that will give you del r upon del x, that will be a x upon r. Same manner, del r by del y, that is y upon r, and del r by del z, that is z upon r. Now we need del u by del x. So again applying the chain rule, that will give you du upon dr into del r upon del x. Correct? Now u is not given, so f has a derivative f dash, so f dash r into del r by del x has a value x upon r. So you have del u upon del x is x f dash r upon r. Same manner, del u upon del y, that will be a y f dash r upon r, and z del u by del z is z f dash r upon r. Now del square u upon del x square, that will be a del by del x of del u by del x. Okay, so what we are going to do is, we are going to put the value of del u by del x, that is nothing but x into f dash r upon r. So differentiating x upon r into f dash r with respect to x. So here we are going to separate two terms. First x by r and second one is f dash r. So applying multiplication rule, that will give you first f dash r as it is and derivative of x by r with respect to x, that will be u by v rule. So r as it is derivative of x, that will be 1, minus x as it is derivative of r, that will be del r by del x, divided by r square, plus x by r as it is and derivative of f dash r is f double dash r into del r by del x. Now put the value of del r by del x and simplify by taking LCM, that will give f dash r into the bracket r square minus x square divided by r cube plus x square upon r square into f double dash of r. This is your equation number 1. Same manner, del square u upon del y square, that will be a f dash r into r square minus y square upon r cube plus y square upon r square into f double dash of r. And same manner, del square u upon del z square, that will be a f dash r into r square minus z square upon r cube plus z square upon r square into f double dash of r. Now add these three equations 1, 2 and 3. So for left hand side we have del square of u upon del x square plus del square u upon del y square plus del square u upon del z square. And in right hand side f dash are common from first three terms, that will be give you 3r square minus x square plus y square plus z square divided by r cube. And from second three terms, we have f double dash r common out. So that will give f double dash r into x square plus y square plus z square upon r square. But x square plus y square plus z square is nothing but it is your r square. So by simplifying, by putting r square and simplifying, that will give you 2 upon r into f dash r plus f double dash of r. So this proves our result. Same manner, if this is example is asked for only two variable, if r square is equal to x square plus y square, and if u is a function of r, then prove that del square u upon del x square plus del square u upon del y square is equal to f double dash of r plus 1 upon r f dash of r. So you have to use the same method by repeating the above steps of example. Only you have to eliminate the term of z. So that will give you the answer of this example. Okay. So these are the topics which we have covered today. If you have any doubt or any query regarding this topic, then please feel free to contact me. Thank you.